So good morning to everybody, except from the person that made me speak so early. My brain doesn't work before 10, so anyway, let's try. So I'm going to speak about RISC-V and EuroHPC and how we are going to power Europe's future in high-performance computing. So I'm very happy to be here and interacting a bit with a slightly different community. So from one niche community to another niche community, I will give, let's say, an overview of who we are and what we do and how space might help us. So let's do this. So who are we? We are an EU body and a legal funding entity. We were created in 2018 and we are autonomous almost for 5 years. We are toddlers. We are based in Luxembourg and we are already a team of 45 employees and we are still growing. And we organize around 7 pillars and AI factories is the most recent pillar. Maybe you have heard this around. So what we do is that we procure systems. So we procure traditional HPC supercomputers. We procure quantum computers. All of these are state-of-the-art systems, and we provide access to European users to the systems. We have applications projects. So we create projects that's around centers of excellence on algorithms and software development. We collaborate with third countries, and the collaboration is always something that A, solves a global challenge, and B, strengthens EU competitiveness. So it can be, for example, in quantum with Japan. We do federation and hyperconnectivity. So we create a federation of our European resources where the users will eventually have access. We have a lot of training programs because we understand that there is a skills gap and we want to basically create in Europe HPC skills. And then we have also the RNI activities. So we develop hardware components, we develop pilots that integrate these components. We have software stack projects. We integrate our quantum resources, and so we always are around energy efficient HPC systems. And now as I said, we also have the AI factories where we basically also procure AI focused systems. A few words about our fleet. So now we have around 10 supercomputers all over Europe. 3 of them are in the top 10 in the world. This is Lumi in Finland, Leonardo in Bologna, and Mare Nostrum in Barcelona. We have 5 smaller systems, and now we are setting up our 2 exascale systems. This is the Jupiter in Jülich and Alice Lecoq in France. And of course, we always have upgrades to the current systems because, a system becomes obsolete after a few years. So we always are designing an upgrade. Then we have also a fleet of quantum computers. We have already selected 8 quantum computers all over Europe. This is at least 30 countries are participating in these procurements. And we also have 2 quantum simulators. Now, at this stage, we are finalizing the procurements, and the first quantum system is planned to be operational later this year. And of course, next to the quantum computers, we also have all the middleware technologies and quantum excellence centers. And also now we have the AI factory. So now every few months we have a cutoff. We have an open procurement procedure for AI factories. And AI factories is a more abstract concept, and this means that it can be an AI-ready EuroHPC supercomputer or an AI upgrade to an existing system or AI optimized supercomputer. So at this point, we have already 13 AI factories as well. So as you see, we are a bit busy for a team of 45 people. And how we are organized. it's a very common mistake to be mistaking that we are the commission, but we are not the commission. We are funded by the commission, but we are also funded by private members and participating states. This is the 34 participating states is already outdated because Switzerland has also joined us recently, and UK. And so what we do is that the European Commission, the private members, and the countries consolidate, give us money, and we consolidate these resources. And at the end, we have investments in the scale of billions. So per 6 years, we have at least 7 billion euros in investments, and this allow us to have at least 2 billion euros that is dedicated specifically to RNI. And what we do with this, we take this investment and we transform it into Digital Europe and Horizon Europe projects mainly. And this means that we have more than 40 research and innovation projects that we run that are on this around these 7 pillars, and mainly on application, skills, and technology. And of course, I will focus obviously on the technology pillar. So the research and innovation part, we are organized, as you see, as in the computing stack. So on the top level, we have this leadership in use and skills. As I said, we build skills in HPC in Europe. We have the national competence centers that are installed in each European country, and they run training programs. And on top of that, we have summer schools. We have a master program that runs all over Europe, and a lot of activities like this. Then we have applications and algorithms. So here we have the centers of excellence for HPC applications for exascale and post-exascale. We are also focused a lot on the software stack. So we're supporting projects that deal with software, with algorithms, programming models, libraries, everything. And of course, the European hardware. So this centers around more or less 5 to less than 10 very, very large actions that are focused around designing chips. All of them are around low power, high end general processors and accelerators. We have a strategy. So we have this big ambition that by 2030, we want 20% of the world production to be cutting edge sustainable semiconductors designed in Europe. We want manufacturing capabilities by 2030, not now, below 5 nanometers and aiming at 2 nanometers if the technology is stable at that point. And of course, since we're talking about supercomputers, we want energy efficiency 10 times more than today. And we have seen two things that we consider that are changing the scenery. One is RISC-V. So RISC-V came and changed let's say, our strategy and our scope. So we see that RISC-V plays a central role in our strategy, and the AI needs are reforming the strategy in processors. So to break it down a bit, we have this in three. The timeline is divided by three: so short term, medium term, and long term. So short term is where we are now, and we want basically to build on the European Processor Initiative efforts. Now we are going from test chips to high TRL. EuroHPC always supports high TRL activities, and we want RISC-V processors and accelerators that are always chiplets and advanced nodes, and we want EuroHPC exascale systems to be the first customer as we scale to embedded. Then we have the medium term up to 2030, as I said, where at this point we envision new RISC-V architectures that complement the work of our main big projects that I'm going to speak in a few minutes. So at this point, for the medium term, we want pilots on RISC-V with standalone processors and accelerators. And we want this to be a collective effort that is building on European R&D, focused on low power and AI. And then at this point, the EuroHPC, at this point, will have the post-exascale systems, and these systems are going to be the first customer. And then the long term, we dream here, and we want post-exascale RISC-V system based on European R&D and ideally manufacture in Europe. Where we are now. So now we are at this point, we are in the last year of the European Processor Initiative. Now we, as you see, we have this, at this point, we are mainly focused on ARM, because ARM is a technology that has been there for many years, and it's a more stable and complete ecosystem. And already we have some RISC-V actions. And we want to go to a state where this is balanced. And I always say that we don't see ARM and RISC-V as competitors, but we see it as two complementary roadmaps. So we consider ARM the more short-term ecosystem that is there. We consider, even though ARM is not European, we consider it European because we have the whole ecosystem around it that is very much European. And then, while we have this on the short term, we give some time for the RISC-V community to become more stable, increase the TRL, and have eventually the RISC-V components. So that's we have, and we organize this around two very large projects. So where we have been as EuroHPC, when we started, we started with petascale and pre-exascale supercomputers, and what we were doing mainly is that we were procuring code systems that were available on the market and using these systems. Where we are now is that we are now at the point that we are deploying the exascale supercomputers and we're starting to integrate European technology. We have the strategic roadmap that designs and delivers energy efficient open hardware technology, and as I said, where we want to be by 2030, 20% of world production to be European tech. And in order to achieve that, we do this with two big actions: the European Processor Initiative that is setting the base, as I said, both for ARM and RISC-V, and the DARE project, that is the very large scale European initiative for HPC that is based only on RISC-V. And here to show you a bit the scale of investments. So here we have, if you see here the MIP was a 10 million euro action that was basically an FPGA cluster that we have it at BSc, and we use it as a basically as a prototyping machine. We have the e-processor that is the smaller action, but is building a RISC-V out of order core. Then we have the EU pilots and the UPEX, that these two are pilots, and they feed from the European Processor Initiative, that is the longest term action of 6 years now, that is creating the processors and accelerators, and feeds to the European pilot, that is the RISC-V system, the RISC-V pilot, and to the UPEX, that is the ARM system. And then we have started the RISC-V DARE, and if you see the scale of investment for European standards, if I'm not mistaken, is basically the biggest Horizons Europe project that was ever launched. Only the phase 1 is 240 million euros, and if it goes well, there is going to be phase 2. And all these projects make an IP portfolio of accelerators and processors, and all of them, the target is that all of them have to be silicon proven, all these projects. So to put a bit this more into context, we have the accelerator roadmap that has started already already in 2021 at EuroHPC. And the goal is that soon it should be competitive with the state of the art. We have the CPU roadmap that started a bit later because of some funding issues, but this is now also in line also to be competitive by next year with the state of the arts. And then we are having now, as I said, the RISC-V and the AI have disrupted the original strategy. So we have integrated this in our strategy, and we built more and more RISC-V IP with the goal to have in 2028 a European supercomputer based on RISC-V post-exascale. Yeah, so let's talk a bit about the ecosystem in more detail. As I said, the European Processor Initiative, we could consider this at the front and center of our chips actions, as I call it the EPI umbrella, that has the RISC-V part and the ARM part, but it's not only that, of course. So we have test chips, we build prototypes, we have a whole emulation system, and also at the same moment, we built the skills in Europe that we had a gap, and also we do a lot of dissemination activities to 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 invite more people to join these actions. So, as I said, this is the EPI, and around it we have on your right side you can see. Actually, it's your left side. On your left side, you can see the RISC-V actions, and on the other side, you can see the REA family with the ARM actions. And you see the difference that RISC-V will be on some pilot systems, but ARM is a bit further ahead with a goal of probably being deployed in actual supercomputers next year. Okay. The core of these actions is the EPAC accelerator, and we also have some people in the audience that have contributed to that. Here we have the vector processing unit, traditional HPC processing unit, and the stencil accelerator and the embedded FPGA. And as I said 2 minutes ago, EPI has a whole ecosystem where they create a new architecture. They have a setup where basically they do hardware software co-design, they validate the new architecture, and they create the new chip that is tested. And in that way, there is a circle where they create new architectures that can be fed then to the pilot projects. And this is basically the new, let's say, cycle that the European Processor Initiative has set up in the last months. Now, as I said before, EuroHPC is a high TRL activity, so we don't just do a proof of concepts. The goal, the aim is to have at least a test chip coming out of the actions. So now the European Processor Initiative is on the second generation of the EPAC accelerator, and then the EU pilot has two different paths. One is with a vector accelerator that will be a tape out soon, going out. Already we have the test chip that came back and is functional on 22 nanometers by Global Foundries, and it is going now towards 12 nanometers. And at the same time, we have the MLS. So the MLS is going to also go into tape out at the same time as the vector accelerator, and the MLS is an AI optimized accelerator, and this will be TSMC 7 nanometers. And if you want to know more about it, also about MLS, you can ask Frank, that he's somewhere. Yes, he's here. So questions to him. And then, of course, we have also the smaller project, eProcessor, that we just had the test chip back that is also functional. This is a smaller project, that's a smaller chip. Global Foundries 22 nanometers also came back, functional, works, we're happy. Yes, RISC-V roadmap. So where we are now, we are, as I said, we are now at the moment that we have some IPs that are becoming more and more stable, and we are building the software stack. This is also going well, or at least that's what the projects tell me, you know. Yes, and we are building also the applications. Then, and now we are going towards commercialization. So, and industrialization. So now we are starting basically to mature and to go towards higher TRL with our new activities. And as I said, we are at the R&D phase. This will be soon completed if everything goes well. Within in less than a couple of years will be completed, and then we are in the pure pilot phase, first pilot systems before the final phase, that is the deployment phase, where we're going to have the pilot competitive nodes go into the supercomputers. How we're going to do that? Now, as I said, I have been talking about 18 minutes already about the whole ecosystem. So the whole idea is that all of these actions are all of them go into DARE. DARE is the digital autonomy with RISC-V in Europe. It's led by BSc. And we have at this point all the expertise that is going from the chip JU, from Tristan and Isolde, all of our projects from the European Processor Initiative, EU Pilot, UPEX, the Mont Blanc projects that came before EPI. We have the HADEA projects, the DEEP, the RISER, and with the support of RISE and RISC-V International, all of this goes into the DARE project. That is a very, very competitive project with an extremely aggressive timeline, with a goal of deployment into supercomputers. Yeah. How we are going to do that? We have three phases. The third phase is outside the scope of the project, but we have a framework partnership agreements. And as I said, only the phase one is the 240 million euro action. And this is organized horizontally in different technical areas. And we have the coordination, and then we have the hardware technical areas that are going to produce a processor and two accelerators. One will be the vector accelerator that we need for HPC, and also the other is going to be the AI accelerator. And then we have integration and prototyping. This is also consolidated and horizontal. And of course, you have the whole software stack as well and applications. And as I said, this is a very aggressive timeline. So the project started this month. In month 18, we have RTL freeze. We have a go-no-go. And the moment we are sure that the IP is mature enough, we go into tape out. And the tape out is, we have two requirements, chiplet-based and advanced nodes. Advanced nodes means less than 5 nanometers. And then we are going to have a silicon in package bring up by the end of phase one. In the 3 years, we expect the first 3 chiplets to be there, back and operational. Yes, of course, since now we are basically in the RISC-V for space, one cannot ignore the fault tolerance of these massive systems. We have some similarities with space electronics, and by some similarities I mean we have the same faults, we have the same errors. So again, we observe in HPC, we observe DRAM errors, we have aging errors, we have permanent faults, we have transients, we have small delay faults, we have the whole range of faults. We have silent data corruptions. This can be radiation based, they can be based on silicon defects, they can be based on electrical marginalities. And don't forget that we are speaking about very advanced nodes, and we're talking about 5 nanometers or less, and this means more defects. And we have the same faults, but we have different we have different origins of this fault. So a radiation effect doesn't necessarily cause an issue on HPC electronics. But at the same time, we have a different way to mitigate. So we cannot afford to do this by hardware. It is more expensive, and we're talking about energy efficient and high performance systems. So traditionally, this has been done with algorithm-based fault tolerance, so on higher levels. However, the problem is very big. Since the scale is completely different, we are talking about our exascale system, we're talking about more than 1.7 million cores. This means that since the mean time between failure can say that it's 100 years, this can mean that worst case scenario, maybe you can have like a failure every 47 minutes. So you cannot ignore the problem. But since you cannot ignore the problem, but you cannot always do mitigation because you lower the performance, then you have to deal with the co-design approaches, with cross-layer reliability, with AI-enhanced methods. You have to use AI since you have it available. So the DARE project is not a project that focuses on fault tolerance, but we are aware of the issue. And what we do, we have this pathfinding track so we have this aggressive timeline for 90% of the projects, and then we have kept 10% of the project, that is still 24 million euro actions, for pathfinding, for low TRL activities to leverage from the project and mature enough. So we have, for example, Politecnico di Torino is going to install aging monitors. They're going to locate the best possible locations in circuitry to install aging monitors. We have Forth that has CAS protection. We have BSC that already is working for many years on error correcting codes and fault tolerant VPUs. So we have we have PISA that is going to discuss later about RERI is there, and we have the silent data corruptions by the University of Athens that are going to install to investigate cross-layer reliability and how the silent data corruptions propagate to the output. And how they're going to do that, as I said, we have to deal with cross-layer approaches, since dealing with fault tolerance on layer-by-layer basis is not always possible for HPC. We're also going to investigate things on cross-layer and deal with how they propagate to the output. We can see how we can adapt with increasing fault tolerance on lower layers. So that's what we're going to do. So as I said, hardware technical areas, aggressive timeline, chiplets and advanced nodes, and at the same time, the technical area leaders are going to give access to the pathfinding track to do research activities on how they can increase the space tolerance, the fault tolerance. This is the partners, as you see, is a massive project, so almost all Europe participates on that. And to conclude, as we said with Andy Moore last year at HighPeak, RISC-V is inevitable. We need inclusiveness in participating in access from academia and industry, but we need to do this with cutting-edge technology and nodes. Faults in HPC systems are also inevitable, and here we need knowledge transfer from the space community to help us increase the fault tolerance of the advanced nodes of the systems, and we need a consolidated effort of all possible European projects to spill over into our new project. And of course, we always need to have a clear, ambitious, and updated roadmap. And with this, I conclude my talk.